right, examples of finding pH. All right, when you do this, there's two things you got to keep your eye on. You got to keep your eye on the moles and the liters, because both of those affect the concentration of the acid or the hydronium. Okay, so let's do an example. Let's say we're going to take 0.03 moles of, let's use nitric acid. So that's the number we want, right? Fix that in your notes. HNO3 in 1 liter of water. Okay, so we have to look at the moles and we have to look at the liters. Now the moles, let's do the moles first. What we have to do is we have to write the equation of HNO3 aqueous, and showing that what it dissociates into are hydronium ions and nitrate ions. Aqueous, aqueous. Okay. Now remember that this stands for these hydrogens that are popping off of the nitric acid, and they are riding on a nearby water molecule. So that's really just an H, right, in our mind. But we have to remember that it's riding on the water molecule to make the hydronium. Okay. You'll also notice that there's only one H, so I'm only going to make one hydronium. So my ratios are 1, 1, and 1. We don't have to write the ones, but we put them in for today just to remind us. So that means I can figure out the moles of hydronium, because that's the key thing. This is the acid part, the hydronium. So if I have 0.03 moles of my acid, because that's what it said right here in the question, and it's a 1-to-1 ratio, I should have the exact same amount then of the hydronium. So now I know how many moles of hydronium. So I figured out the top part of my concentration number by using the ratio. If the ratio was different, 2-to-1 or 3-to-1, I would change that number, right? If it was a 2 right here, I would make it 0.06 or whatever the case may be. Now the other thing I have to watch is the liters, and I have 1 liter of water. So this is an easy one, because that means now my concentration of hydronium will be 0.03 moles in 1 liter, or 0.03 moles per liter. And then I can do my pH equation. pH equals the negative log of the hydronium ion concentration. Now some people in some textbooks, they'll write H plus here instead of H3O. And that's okay too, because really we're tracking that hydrogen, right? But remember, the hydrogen always rides on a water molecule and makes hydronium. So I prefer to use hydronium instead of the H plus to remind us of that. Anyway, we put in our numbers here. So pH equals the negative log of 0.03 moles per liter. And that's easy to figure out on your calculator. Just take your calculator. You have to figure out which way your calculator works, right? And what you should get is about 1.5 if we round it off. So there's the pH, 1.5. So on the scale, that's way down on the acid side. That's what we expect, because we added nitric acid, so we expect it to be acidic. Okay, we'll do another example where the ratio up here is not 1-to-1, and we have to change the number of moles that we're dealing with. All right, so the next example will be phosphoric acid, H3PO4. No, sorry, not that one. Let's stick to certain acids that I know will work. Let's do sulfuric acid, H2SO4. Part of the problem is that some acids, they don't actually give all their hydrogens up. There's kind of a back and forth. And you'll learn about that next year. So you have to be, I have to be very careful of which acids I pick. Let's put a number here. Let's go 0.0007 moles, a very small amount. Okay, and we're going to put that in 1 liter of water. So we'll keep the 1 liter for this example. And we want to figure out what is the pH. That's the question. What's the pH of this, okay? So the first thing we have to do to get the moles is we have to write the equation of what happens. The H2SO4 is going to break apart when we put it AQ in the water. That means those hydrogens are going to come off, and they're going to ride on the waters to make hydroniums. And the sulfate ion is going to be free. But we have to be careful in our balancing here. There are 2 hydrogen atoms here that will break off, and each of them will ride on a water molecule and make 2 hydroniums. So my ratio here has changed. It's gone from, it's a 1 to 2 to 1 ratio. Okay, so that means if I have 0.0007 moles of this acid, then the hydronium is going to be twice as much. So I have to multiply it by 2 to get the proper amount of moles. So that's different from the last one. So you have to watch how many hydrogens there are in the acids. That's kind of important. Okay. Then I now know the moles. It's twice as much. I check my liters. Well, it said 1 liter of water, so that means that the concentration of H3O plus, or hydronium, is 0.0014 moles per liter. So on tests, a lot of people forget about this, and they just use 0.0007 by mistake because they didn't do the first part properly. Okay? So now I can do the pH, the negative log of the hydronium ion concentration. And so that would be pH equals the negative log of, I'll go back up a bit, 0.0014 moles per liter. And if we take our calculator out and we crunch that through and we put 0.0014 and we do the log, we get a pH of about 2.85. So it rounds off to about 2.9. That's not quite as acidic as the first one. I think the first one was more than that, eh? What was the first one we did? The first example was 1.5, and this is about 2.9. So this is much less acidic in this case. And that's because we started with smaller amounts of moles, right? Okay, now let's do one more example. And this time I'm going to change the liters. All right, so let's do one more example. Let's say we have 0.0062 moles of chloric acid. Chloric acid in 0.6 liters of water. That's not quite 1 liter, is it? Let's find the pH of this solution. Well, let's get the moles first. HClO3, AQ, is going to break up. So those H's are going to come off. And they're going to join up with waters to make hydroniums. And if the H's come off, it will leave the chlorate ions by themselves. So these would all be aqueous. So there's my equation. Now I have to check for balance for numbers. There's only one H here, so there will only be one hydronium that's being made. So what I have is a 1-to-1 ratio again for this acid. So that means if I have 0.0062 moles of the acid over here, the red numbers, the ratios are telling me that I have to have exactly the same amount of hydronium moles, right? Now, here's the catch. That's not in 1 liter. It's in 0.6 of a liter. So here I have to say, okay, the concentration of my hydronium is 0.0062 moles, but instead of being in 1 liter, it's in 0.6 of a liter. So all I have to do here is a little extra division, right? I have to divide the 0.0062 divided by 0.6, and what that turns into is 0.01 moles per liter, rounded off. So you see how we had to change it. We had to do a little dividing because I didn't have 1 liter to get the concentration. So we can change the top number or the bottom number, and we have to be ready for that. And then you do the pH, which is the negative log of the hydronium ion concentration, which would be, in this case, the negative log of 0.01, right? So our concentration was a little bit different because we had to divide by the liters to get it per liter. It has to be per liter on the bottom for concentration. Okay, and then we just do our 0.001. This is an easy log you can actually do in your head once you understand how logs work, because it's a 1, but I won't get into that. This comes out to a pH of about 2. So there's 3 examples showing you the different ratios that you have to watch for the moles, and also what to do if you don't have 1 liter. You have to divide, right? You have to do that division. And that's how we can calculate the pHs of certain acids. All right? Only certain acids that completely dissociate, that completely follow this pattern where they break apart completely, can be done this way. Some acids don't completely break apart. They break apart, but then they join back together, and break apart and join back together in like a little dance, an equilibrium dance. And that means it's harder to figure out how much hydronium is actually there. Those acids are things you'll learn about in grade 11. So we're just learning the basic intro, and it works for these particular acids. These are called strong acids because they completely fall apart like this in the water, and they don't go back together. All right, there we go. There's our examples. The last